talk about a definite integral, and then the definite integral will be defined as a limit of Riemann sum. So the Riemann sum, we already introduced the idea to you. I can just use this. I can use this to just remind you that the concept about the Riemann sum. The so-called Riemann sum is when I give you a function y is equal to f of x, and I also give the focus interval from A to B, right? Then based on the interval A to B, I can randomly pick up n minus 1 points. So when we just including these two n points, x0 and xn, that means A and B. Totally, we will have n plus 1 intervals, subintervals. So then we can just divide the whole interval AB into n plus 1 subintervals. So you can see the subinterval will include S0 to S1, S1 to S2, blah, 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 and so on and so forth to Sn minus 1 to Sn. That means B, right? So totally we have n subinterval through this n plus 1 points. And in each subinterval, we will randomly pick up 1 point within this subinterval. Take the first one as an example. For S0 to S1, I pick C1. S1 to S2, I pick C2. Randomly. Okay? So after we just pick this point, we just use this point to be the sample point and use it as an input. Then we just use the input for the function f of s, then we can get the function value. Like here, we will get f of c1. F of c1 will be used as the height for this rectangle. But just notice that the so-called height here is about the function value based on this sample point, this picked point. So the height here will be maybe positive or possibly negative. Not like when we want to calculate the area of the rectangle. Normally, I shouldn't say normally. It should be height should be positive and width also should be positive. But here we will allow the height could be a negative value because we just use the function value as its height. So taking this example, here we will contribute something negative. Here also contribute something negative. Okay, so based on this idea, we can just calculate all areas for these rectangles and then sum them together by this one. Then we will say this is the Riemann sum for this partition. So you can just image that if the partition is different, the corresponding Riemann sum will also be different, right? Because the partition can be very, very random, and especially the C1 to Cn and also can be very random. So based on this P, based on the C, then we can have a different Riemann sum. Okay, so that means if I give you a function y is equal to f of s, and I also give you an interval, focus interval on A to B, that there are many Riemann sums because the partition can be varied. The pick points are also be varied. So that means there are so many Riemann sums. And besides, next time we will talk about the idea about the norm of P. Norm of P means the largest part, largest length of the all subinterval. So you can see, I also give you an example that based on this partition, you can find is known. That means the largest width for these intervals. Okay, so after I review the concept about Riemann sum, you already have the idea. Then, if we want to define definite integral based on the limit of Riemann sum, we just give a very precise definition for the definite integral. That means if I give you any epsilon, then I always can find a delta corresponding also. The delta will be used to constrain the partition. So when all partition, all widths for these subintervals are less than delta, then we also randomly pick ck for each subinterval. Then this Riemann sum will be very close I. No matter how you pick this point, within this constraint, you always can make this value very close to this value. Then we will say I is equal to the definite integral of f(x) from A to B. 所以上礼拜我们这礼拜一哈，我们讲的定积分，它是来自于这个黎曼河哦。那记得，反正这里的概念就是跟我们在学那个 precise definition 一样，它就是在勾勒一个所谓的接近的概念，对不对？那但是那个当初的接近的概念是我们是limit s 趋近 S0 f(x) 等于 L 的时候的那种接近的概念，就是只要 S0 非常接近 S 非常接近 S0， 它所反映出来的函数都要非常接近 L。还记不记得 precise definition 背后的意义，对不对？所以同样的把这样的概念应用到定积分来想，事实上也是这样，就是说我们在做这个黎曼河的时候，它是有千百万种的不同。这不同取决于什么？它的 partition 取决于它不同的 C 的取法，对不对？但是呢，假如它是一个定积分，是可以计算出来它的值的话，它一定拥有一个满足这样的一个定义。怎么说呢？你看他说你的 partition 如果是这样切，当我任意给你对，应该这样说，我任意给你一个epsilon，我可以找出一个 delta。注意这个 delta 在过去 S 趋近 S0 的时候，我们是用来规范 X 的范围。这个 delta 在定积分来是用来规范谁？规范最大的区间的那一个，最大区间那个长度最大的那个，对不对？所以我的最大区间，我一定永远你给我一个epsilon，我可以找到一个 delta 来控制你的 partition， 也就是这 partition 不是只是随便乱切。切完之后，你还必须满足它最大的那一个子区间宽度呢，必须小于这个 delta。那而且呢，在这样的选取的子区间的条件下，你任意去挑这些点，这些点用来带出它函数值当做它的高的时候，去把它加总起来呢，它跟 I 的值一定会小于它的绝对值，也小于这个epsilon。所以大家如果去映射过去讲到极限的概念的时候，我们是用 用 delta 来形塑那个 S 非常接近 S0 的时候，所以同样的这个 delta 事实上也来当你给我一个epsilon，我可以找到一个 delta， 事实上我也是用这个 delta 来控制我的切割区间最大的那一块应该整能多长，对不对？那如果在这个限制之下，它能够保有这两个之间的值非常接近，那记不记得我们当初在讲，这就是一个我们的目标是 S 趋近 S0， 代表什么？我这epsilon既然可以随便给，我可以给的非常大，但是我也可以给的极度小。我给的极度小，所映射出来的 delta 也会非常的小。那我如果映射出来的 delta 非常小，牵扯到的就是我切割的那 partition 的子区间最大的那个也要非常小。那非常小，小到什么？接近0，代表什么？我最大切割的点的那区间的长度，最多就接近0，那代表什么？所有的切割事实上宽度都是接近0的。我用一个 譬喻来说，我们班考最好的那个同学成绩接近0，那代表什么？不是像你们不是期中考，但最好的成绩接近0了哈，是说代表什么？就几乎大家都考0分嘛。最好的同学考最好那个同学接近0，所以同样道理，当我们用这个 delta 来 constrain， 用这个 epsilon 来 constrain 它的时候 ，epsilon 非常小的时候，你可以想象这个 delta 一样非常小，小到每一个人都接近0，每一个人都接近考0分，那是不是一种无限切割的概念？对不对？只有在无限切割的时候，那他们呢，它的加总啊，还会跟这个 I 啊非常的接近。那我们就说它的定积分是这样。Okay, so based on this concept, you can see we can randomly partition, but the partition should be within this constraint is known, must be less than delta, so that if we can have so many partitions, the base case, if we want to make the computation be computable, that means the equal divided method could be the best one, and especially it is computable. So I will show you. So we will start today's idea that I will show you an example that if I ask you to calculate, please just compute integral from 0 to b x dx, and find the area A under y is equal to x over A to B. So we already know the notation for the definite integral. This is the integrand, right? This is the function, right? This is the interval 0 to b. So based on this, we can simply draw this function on the plane. Actually, we are talking about this one from 0 to b. We are trying to get its definite integral from 0 to b based on this function y is equal to x, right? So we can try to solve by using the idea about Riemann sum. Okay, so based on this, we can try to have a equal divided method. So we can take delta sk as b minus b over n, right? If each delta x, we just set it as b minus 0 over n. That means I am trying to divide the interval from 0 to b equally and into n pieces, right? So I just try to divide it just like this way, and then each piece just b over n, right? And especially for sk minus 1 to sk, for this part, the typical part, its length is still n b over n, right? And for this subsegment, for this this piece, if I just equally divide it as this one, then because I need to pick up one point, right? According to the Riemann sum, we divide interval into many subintervals. But for each subinterval, we need to pick up one point. Why we need to pick up this point? Because we pick up this point, we will use its function value as the length, the height for this subinterval. So we just choose CK to be the right endpoint. So that means finally I decide I just use this point as my CK. For this subinterval, I choose this one. For this subinterval, I choose this one. For this subinterval, I choose this one. So I pick CK to be the right endpoint in each subinterval, so that my partition will be 0 b over n to b over n, then kb over n, then m over nb, right? So here you can see this one is my sk. This is my ck, and this one is this one is my p point, and also that ck I just put as kb over n, right? Because I already choose the right endpoint. Of course, when you go home, you can just have some kind of exercise by yourself. You can just try to pick the left endpoint, see what will be different. See something else will be different from this one. But at this time, we just pick the right endpoint as is CK. So therefore, we can just try to calculate its Riemann sum, right? So K is from 1 to n, f of CK. Here, this is CK times delta SK. So it will be sigma K is from 1 to n, f of CK, since it's linear, so the result will be KB over n. Because f of s is equal to x. So when I use CK as the input, we will come out CK there. So CK is KB over n, so the result will be KB over n. Then times for each segment, it should be B over n. So finally, we need to solve this. It will be K B squared over n squared. Since these terms are constant, right? So we will become B squared over n squared times sigma n from 1 to K is from 1 to nk. So times this part will be 2n times n plus 1. Right? This part is because of sigma k, so we can get it one. This part, because it's a constant, we can move it out of this summation, right? So that the result will be this one. Then we can continue to get that. We can get b squared over 2, then 1 plus 1 over n. So finally, the result will be like this one. So as n is approaching positive infinity, so that means even though it's an equal partition, however, I try to make it into infinite number of pieces. So that means n is equal to positive infinity, because we are trying to make P known is equal to 0. Because when we just force P known is approaching 0, that one possibility is we just force n is approaching positive infinity, right? So that we can see integral from 0 to b s ds will be b squared over 2, right? Because you can see if n is approaching positive, then this part will be vanished. This part will be vanished. We will have b squared over 2 left. So the result will be right. So finally, actually the result is this one. And we also can verify that, find the area under y equal to x over a to b. Oh, sorry, here should be 0 to b. For 0 to b. So from this, I believe that will not be a big problem, because if we want to calculate the area under y is equal to x over 0 to b, that is not that hard for you to calculate. That should be b times b over 2. So the result is still the same, right? So you can see here are the same. So it is equivalent to try to the integral, the definite integral is equal to calculate the area under this curve within x-axis and the y is equal to x function. Then we can suddenly find that the result is just like b squared over 2, right? So if you want to extend it to, so how about if you have this result, how about integral from a to b s dx. So actually you can see if you want to calculate this, it will equivalent to, here is still b, but here is a. This time I just calculate this part. I just want to calculate this part, right? If I want to calculate this one. So actually it will become to b squared. The answer will be b squared over 2 minus a squared minus 2. Because you can see, if I want to calculate this part, I can calculate the whole part first, then minus this part. So we can easily extend the idea to calculate integral from a to b x. Then the result will be like this. You just reply the result twice, right? One is for this one, one is for the larger one, one is for the small one. Then you can get the result. Okay? So this is a very typical example for the definite integral. I think that is not hard. So let's just continue to introduce the integrability of continuous function. So if a function f of x is continuous on AB, and f of x, or sorry, I should say or f of x has at most finite finitely many Jenq discontinuity there, then the definite integral from a to b f of s dx will exist, and f of s we will say is integrable over ab. So did you remember when we just learn differentiation, we will learn about what is differentiable. For the integration, here we also learn what is integrable. But did you remember? Oh, let me just remind you. We just mentioned that if this function is differentiable, we will say the function must be a continuous function, right? And I also talk about that a function which is continuous, it doesn't mean f of s is differentiable. Here we are talking about integrable. For integrable, if the function f of s is continuous on this interval ab, if it is continuous, okay, it should be an integrable function. But another case is if f of s is not continuous function, but it just has at most definitely many Jenq discontinuities, then in such a case, this function is still integrable. 连续函数一定可以积分，即便连续函数它不是一个连续函数，只要有限个许多跳跃不连续点，它还是可以积分。但是前提是它必须要有限个许多不连续点。好，再讲一次，只要是连续函数，它一定可以积分。但是如果万一遇到不是连续函数，但是它只有限个跳跃点，这种情况还是可以积分。一种情况不行，它如果它的点是有无穷多个跳跃点的话，这种不连续函数就完全不能积分。Okay, so let me just show you an example that, for example, in this case, maybe for this case, I can tell you that, for example, if the function just read like this, you know, in this case, it is because we just have two jumping points. This function is not continuous, but we just have two Jenq discontinuities at C and D. So in this case, this function is still integrable from A to B. Okay? So I will show you an example that it is not integrable. For example, if a non-integrable function on 0 to 1 f of s, if s is rational, if s is irrational, if x is rational, I will define the function variable as 1. If the x is irrational, then you will say the function value is 0. So from 0 to 1, how many irrational numbers? How many rational numbers? Infinite, right? 0到1之间有多少有理数？无穷多个。0到1之间有多少无理数？也是无穷多个。那这个函数定义成这样，我要说它就是一个不可积分的。Okay. So we start to prove it. If we say f of s is integrable, so that we can pick a partition P of 0 to 1 and choose ck on each subinterval sk minus 1 to sk. Okay, so the idea is just like this one, like this one. This is 0, this is 1, right? So I just partition it. The spatial here is sk minus 1 to sk for this case. Okay? And this is sk minus 1 to sk. Then ck will be here. Okay, randomly. Okay. Then we try to calculate its Riemann sum. Will be sigma k is from 1 to n f of ck times delta sk, right? Delta sk means the length, the width, delta sk, right? So for each part, delta sk times the function value based on one point ck, f of ck times delta sk. Then we can get this part. Then we just make a summation for all parts. Now we can get the Riemann sum, right? So the typical Riemann sum is just like this one. And then we try to discuss the condition. If all ck's are rational, so that the Riemann sum will be how much? If all of the ck are rational, rational means lower. You can see, if rational, all ck are rational, then its return value will be 1, right? So the result will be sigma k is from 1 to n. The result will return 1 times delta sk. So what is the result? So what is the result? For each piece times 1, piece times 1, times 1, times 1. So finally, from 0 to 1, right? It will be 1, right? Okay, this case is for all ck's are rational. But if all ck's are irrational, so your Riemann sum will be sigma k is from 1 to n. Then the return value will be 0 times delta sk, right? So the result will be 0. 1 is different from 0, right? So it will be conflict. Why conflict? As we mentioned that if E is integrable, that means no matter how you just partition this one, no matter how you pick this point, the result should be the same one. The result should be the same one. So here, did you remember? I just remind you that if it's integrable, all of them will be approaching to the same I, right? But in this case, if you assume it is an integrable function, but based on this analysis, you can see if you just pick all ck are rational, because if it is integrable, it will allow us to randomly pick these ck's. So we choose to pick these ck's as rational numbers, then you can get the result is 1. But in this case, the Riemann sum will be 0. So there is a conflict. Because as we mentioned, if it is an integrable function, all of Riemann sum will be the same, will converge to the same Riemann sum. But here, they are different. So our assumption is wrong. So that means, so in this case, actually this is not integrable. Okay? 这样了解吗？啊，这个例子，这个是一个不可积分的例子。可积分有2种，函数刚好是连续的，或者是它在这个区间里面只有限一个点不连续。这个例子刚好告诉我们一个，有无穷多个不连续点，它一定是不可以积分的。好，那这个函数它把它定义成0到1很有限，对不对？但它有无穷多个有理数跟无理数。那我说这个有理数呢，它就return 1，无理数它是0。所以乘下来结果你会发现，它在这种情况下它的黎曼河是1，在这种情况之下黎曼河是0，那就冲突了。因为如果可积分，它的黎曼河应该要同一个，所以在这里就冲突了。冲突以后就代表什么？我们讲的不可积分是错的。OK。Okay, so I think you can just digest by yourselves gradually, and let's just continue to introduce the second theorem. If f of x and g of x are integrable on AB, then there are many rules I need to show you. The first one is integral a to b f of x dx. It will be minus integral b to a f of x ds. So you can see the start point to end point. If we just reverse it from b to a, you need to add negative sign here. Okay? And the second one, integral a to a, the result will be 0. Because a to a, that will be a single point. So the length for a single point should be 0. So the result, of course, also 0. The third one is integral a to b, k times f of x ds. It will be k times. So it is also easy to be understood that a to b, each item will have k times. So we just simply move the k out of the integral. So sometimes you can just regard integral is a continuous form for summation. Did you remember I just teach you summation? Summation means I just add many terms together, right? But if you just use summation, you can regard it as a you are trying to do summation for infinite number of points. Okay, so k, of course, we can just move it out of the summation. And of course, if we have this one, you can simply move minus out of the integral. And fourth is integral a to b f of s, additing or subtracting g of s dx. Then it will be this one. So you can just adding them together or subtracting them together, or just individually calculate themselves. Then we just adding the result together or subtracting them together, g of x. I think this rule is not that hard, so I just simply introduce you and quickly go through all of them. And this one is also important. If A to B, B to C, then through this breakpoint, we still can link them together. Okay. The sixth one is if f of x has a maximum value, we call it max f, and minimum value, we call it min f. Over AB. Then min f times b minus a will be less than or equal to AB f of x dx, and less than max f b minus a. It is not that hard to understand that, so I can show you a figure that if we assume the function here, this is y is equal to f of x, right? There is a ceiling, we call it max f, and there is also a floor, we call it min f, right? So when we calculate the integral from a to b, f of x, so you can easily understand, you can see min f means the size of the area. Min f times b minus a, right? Then this part will be the max f times b minus a. So if you want to integrate f of x from a to b, it will just sit in between, right? So that is not that hard to image that. So you can simply use this one by this one. And then number seven. We call it domination. If f of x is larger than or equal to g of x on AB, then we can say integral from a to b f of x gx dx larger than or equal to integral a to b g of s dx. So especially if f of s is positive or is larger than 0 or equal to 0, then we can conclude that from a to b integral f of s, then the result will also positive. Right? This is just one of these cases. If f of s is larger than 2, so you can regard g of s here as a 0, right? So of course, when you try to integrate f of s from a to b, the result is also positive. Or 0, right? So these rules are very simple. So let me just give you an example that from -1 to 1, f of s ds is 5, and from 1 to 4, f of ds is -2. So first, from 4 to 1 is simple, right? It is just simply minus 1 to 4. The result will be -2. So the result is +2. The second, -1 to 4 can be divided in two parts, from -1 to 1 plus 1 to 4. So the result will 5 minus 2, the result is 3. Right? This is simple. We just simply apply this rule, then we can get the result, even though we don't know what the function is, right? And the last one I want to show you is, please just show that integral from 0 to 1 square root of 1 plus cosine x, it will be less than 3/2. So in this case, if we want to solve this problem, that because cosine x is less than or equal to 1, therefore square root of 1 plus cosine x will be less than 1 plus 1, right? Because we just use this rule to replace cosine x. So that will be square root of 2. So that if we want to calculate the results, that will be less than this one. So that will be square root of 1 minus 0. That will be less than 3/2. Okay, so actually this example are very simple. You can just simply apply the rules in this size, and then you can get the result. Okay, so let's just take some break and come back later. We already know how to calculate the definite integral, right? Based on the concept of Riemann sum. So we need to clarify the difference between area and definite integral. Actually, these two concepts are the same when the function is positive. But if the function is not always positive, that means the function sometimes is positive, sometimes negative for in its domain, then the final result, I mean calculating the area in some interval, or we try to get its area, its definite integral. Actually, they are totally different. So when we just talk about area under a curve, which defined by some function as a definite integral, that will be different. So that means you can see area, definite integral, they are different, but for some case they are the same. So if f of s is non-negative and integrable on AB, then the area under the curve y is equal to f of x on AB will be the same as the definite integral. You can see this case is for non-negative and integrable function. So you can see, I can draw a picture for you that you can see by this one, this y is equal to f of s, and it is non-negative. So that means non-negative means that all function values should be positive or 0. Okay, so in this case, when you calculate its size, actually it is still the same as the definite integral from a to b f of s, right? But if the definite integral is always will be different from the area between f of x and the x-axis. Actually, these two parts are different. If we are talking about, okay, for this part, we are talking about the if we just use the Riemann sum to calculate the result, it will be like, okay, I give you the function y is, oh sorry, maybe this is not a good example. It will be a good example. If we are talking about that, a to b, right? Then you can see if we just follow the Riemann sum. Did you still remember Riemann sum? We use Riemann sum to calculate. We need to partition it. We need to partition, right? And then each piece, we try to pick up a ck. Each piece, we try to pick up a ck. Each piece. And especially, please notice here, you can see here is negative. Here is negative. Here is also negative. Right? So, in some sense, you can see this part will deduct this part. Right? If we want to calculate the integral. But when we just talk about the area between f(s) and x-axis, that we were talking about that the same, right? Here is a to b, but in this case, area between f(s) and x-axis, this is x-axis, and then we are talking about calculate this, right? So they are different. They are different. This part is talking about this area plus this area and plus this area. But this is talking about when you just draw the curvature like this. You just have some subinterval by using some partition point, by using some partition set to divide it into many subintervals. For some subinterval, you can see this part will contribute a negative part to the whole summation, right? Like this part will be deducted. So this part will be deducted by this. Okay. So, for example, in the left case, this part will be positive, right? And this part will be positive. However, this part is negative. But for this one, for area between FOS and x-axis, this should be positive, this should be positive, this should be positive. So in this case, the A, suppose it should be, for example, if we here is C and D, here is C and D, the area will be integral from A to C FOS dx plus from C to D FOS, but try to get its absolute value. Then integral D to B FOS dx. But we just divide it into three parts. This part are positive, just keep it the same. But for this part, since it will come with a negative value, so we need to get absolute value. Okay. So, but for the left-hand side, it just simply A is from A to B FOS ds. Okay, so one is this part. If you want to calculate this, one is this part. This is this is so the question mark means only FOS is a non-negative function. It will work. It will work. If FOS is not always positive, then if you want to calculate the area, you can follow this way. If you just want to simply calculate its definite integral definitely integral, you can just simply use it this way. Okay, so this is a very important, even though it's simple, but very important idea. Okay, then we just continue to define what is the average value. The average and the mean value of a function. As I told you, since function is continuous, so there are many points, uncountable, not finite number of points. So if we want to calculate its average, we need to define it as that if f is, please remember, is integrable on AB, then its average value, or we call it mean value, on AB should be average value of f is equal to, try to integral name from A to B by divided by its length. So you can see this is the whole summation, but divided by width, right? So example, please just find the average value of f of s is equal to square root of 4 minus s squared on negative 2 to positive 2. So that the idea is you can just draw the figure for your reference that actually it's a half circle and its radius is 2. So this is y is equal to 4 minus s squared, right? It's as a half, upper half of the circle, right? If you're trying to calculate its average value, again, I just want to emphasize, you can see there are so many points. You cannot simply pick points one by one, then just make a summation by this value and divide it infinite number of points. So we just simply define it as this one. So if we want to get the average value, then we just follow the formula that to do this one. So at this moment, maybe you will say, I don't know how to calculate. Here is minus 2, this is 2, this is 2 minus 2, right? Based on the formula. So at this moment, we still don't know how to do the integration for this one. But you can see, this function is positive. So as I say, if the function is positive, actually when we just calculate its definite interval, that is equal to we are calculating its area. So in this case, you can simply just use what you learned for the calculation for a circle. So it will be like this one. Then for spot is 4, and finally the answer is this one. 好，这里要讲的是什么呢？所谓的函数的平均值。什么叫函数的平均值呢？我们知道函数呢，它不可能像在函数它是一个连续的点所构成的，对不对？所以以这个例子来讲，我们直接用例子来讲，可能更快。以这个例子来讲，你有无穷多个点，你不可能一个点一个点拿出来相加，再去除以它的点数，对，照所谓的平均应该是这个意思嘛。好，我上次讲过，我们全班的平均分数是怎么样？是来自于每个人的分数加总结，再除以我们班的人数的总数。可是对于连续函数来讲，这件事情是不可能做到的。为什么？因为点数太多，无穷多个点，你根本穷举不出来。好在呢，我们就做了一个定义，也蛮合理的。怎么说呢？我就定义成这个函数的在这个范围里面的积分去除以它的区间的长度。好，所以这应该是这个去除以区间长度。那你会看到这个积分根号4加 s 平方，你说目前我们还不会积，对不对？可是还好是什么？因为它描述的是一个正函数，刚好是一个半圆。那正函数刚刚有提到，如果你今天都是函数是正的，你在计算它的积分的时候呢，等同你在算它的面积。但是刚刚讲过，如果这函数有正有负，对不起，你就不能这样做，你就把它拆。可是我们现在遇到函数很幸运的，它是一个正函数，所以当我们在算正函数的时候呢，积分面积跟积分，它算出来的面积跟它积分的定积分算出来的结果是要一样的。所以就这样的原因之下呢，我们把它的定积分在计算过程就把它省略成什么？算它的面积。那我们知道半圆的面积很容易派 r 平方除以2。那分母的部分是它的长度，所以除以4，所以答案是2/2。好，所以这个题目呢，其实是相对的很简单，你不用涉及到什么积分，你就直接算它的半圆面积就好了。Okay, so this is for section 3. Okay, so this is session 3. So we all already reached the half of the chapter 5. Because in total, for chapter 5, we have 6 sections. But right now, we already finished the first 3 sessions. Any questions? Don't forget, next week we will have a second quiz. But this time we just from 4.4 section 1 to section 5 in chapter 4， 第4支4至1到4至5，这样够少了吧？4至1到4至5，对，这样很少了，应该可以好好发挥你们的实力了吧？好好掌握这个机会，把分数减一些回来啊！4至1到4至5，我刚没有讲5哦。4至1到4至5，5 1到5，6是因为它是那个牛顿法，7是讲那个反导函数，所以我们把算的积分，所以就不考。还是大家可以考到这里，这样啊？牛顿法，因为那个我们没办法考，但是其实我还觉得还蛮有趣的，但我们没办法考，所以就跳过去了。而且牛顿法事实上是微积分一个蛮经典的应用的一个例子，你们应该有听过吧？好了，我们去象山的时候来讲牛顿法。Okay, let's just move forward. Okay. Okay, section 4, we will talk about a very important theory. It will be the fundamental theory. Fundamental theory of calculus. 微积分基本定理哈 ，This is very important. Before that, I'd like to show you the mean value theorem for definite integral. So we learned the mean value theorem before, right? Did you still remember what is the mean value theorem? Result for definite integral. Let me just remind you. The so-called mean value theorem is that if this function y is equal to fx, it is continuous from a to b and also differentiable from a to b. We always can find at least one point c, between a and b, and its function value is its first derivative will equal to, when you just link these two endpoints together, when you just link these points together, you will form a line, and then you can calculate its slope. So for the past, we can learn mean value theorem. We are talking about it. We can find at least one c between a and b, and its first derivative f prime c should be equal to f of b minus f of a over b minus a. Here is a f of a, and here is b f of b. Something like that, right? But this time we are talking about for definite interval, so that is different from the previous one. So this one will be if f of s is continuous, it should be a continuous function on AB, then we can find some c in AB, and f of c will be its average value. Did you notice that actually that will equivalent to that I can always find a c in AB such that f of c is equal to average of f in AB, right? Did you notice that this integral from a to b f of s ds divided by b minus ab is the average? And this case, it just happened in a continuous function. In discrete one, actually in the discrete one, words, it not always happen. It is not always happen. For example, in this case, that means I always can find a certain point C in AB, and its function value exactly the same as its average. 意思是什么？在连续函数的世界里面如果它是一个连续函数，我在 A 跟 B 之间，我可以去算出它平均值嘛？还记得吗？这个上页我定义过这个连续函数的平均值，对不对？我可以算出它的平均值，而且呢，恰好就有某一个点，但是这函数它的值刚好就跟这个函数的平均值是一样。这个在连续函数的世界也是可以看到，在我们离散的环境里面，这件事情必然发生吗？未必，对不对？比方说我们班，好了，随便说有一个班级就只有2个人，我跟这位同学，对不对？他比较厉害，他考100分，我考0分，所以我们班这是2个人，我们班平均几分？50分。这个50分有没有发生在他身上？他100分没有啊。这50分有发生在我身上？没有，考0分啊。所以在离散世界里面呢，这个50分是我们的平均值，可是并没有一个人考了一个50分的分数。但这是个极端例子，你去把全班的分数算平均，未必刚好就有那么一个人考了我们班的平均分数吧。可是这个例子，这个连续函数的平均值，在这个所谓的均值定理for definite interval，你会发现，它的意思就是说，在这里面，函数呢这么多点，有这么多的函数值，可是呢，你把它算出总平均之后，一定会有某一个人的平均值到有一个函数值到这个平均值，对不对？就在离散现象，我刚举那例子就是一个没有人取得那个平均分数。在真实世界，就算我们班有60个，有100个，其实这种机会也不多啦。大家刚好考的，比方说我们班平均搞到是，讲高一点好了，让大家，98.55分好了。会有人刚好就是考出来考98.5分很难，可能有人考98分，有人考99分，有人考97分，有人考100分，但是就不会有人考98.55分，懂吗？所以连续函数可以，连续函数就有这个情况Okay. So based on this idea, I will show you an example. Please show that if f of s is continuous. Is continuous on AB, and A is not equal to B, and if integral A to B f of s ds is equal to 0, then f of x is equal to 0 will happen at once. In AB. Actually, we should say it's at least once, because we may possibly find many points. Its average is its function value is equal to the average value. So okay, based on this position, we can say that we already know that average of f, that means the every value of the function should be equal to this one, right? By the definition we just showed in the previous exercises, right? And then you can see, based on this proposition, you can see here is 0. So that means here is 0, right? So that average value of the function should be 0. And as the theorem just showed, that you always can find a C in AB. Its function value is equal to the average, so that we can get we can find a C in AB such that f of C is equal to the average value is 0. So the C is a solution to f of s is equal to 0. So did you remember when we talked about what is a solution to f of s is equal to 0? That means when I use C as the input for the function, its return value should be 0, right? So according to this one, we can get the root, right? 这个例子呢，也可以用来看根。记不记得我们之前的看根怎么做？我们用中间值定理，有没有？连续函数有一正有一负，必定有经过一个零的地方，对不对？那个是说我们是用的是中间值定理，一正一负之间，在这个连续函数的爬升或下降过程，它一定会经过零的地方，或者一负一正的，都可以。那一定会经过零的，我们就说这里面也有根，这我们已经讲了好几种例子，对不对？那这个呢，是用积分的技巧来算出根。它怎么做的呢？它是说，你呢去找到2个点，让它这个定积分起来刚好是等于0。记不记得我刚刚讲定积分是什么？如果这个函数不是恒正函数的话，它一定有正有负或互相抵消的。所以你要去找出2个点，让它互相抵消完的积分值结果刚好是等于0。其实这有点难呢，我觉得有点难。但是如果你可以很容易的找出这种情况的话呢，那恭喜你 A 到 B 之间就一定会有一个存在一个这个函数的根。它的证明方式就是这样子。但是我说它要应用起来确实是有点难，为什么？因为你要找出对一个函数做所谓的定积分，但是它的 A 到 B 又不确定，但是你的要求是积分完要等于0， 这个我觉得有点难。但是假如你可以做到这个境界的话，你就达到 A 跟 B 之间必定有一个根，因为一定会有一个 C， 它的值会等于这个平均值，而这平均值等于0的情况之下，那这个 C 就是等于它的根，它的解了哈。OK。Okay, so we just move forward also for the if f. So I will start to introduce the fundamental theorem part 1 to you. If f of t is an integrable function on I and A belongs to this I, but it's a fixed point. And I also have another point x belongs to I. It is variable. Okay? So we can define a new function, big F of x. We define it as f of x is equal to integral from a to x f of x dx by this one, this big function s and y. Suppose it should be t, just because s we will use for other purpose. So here is y is equal to f of t, right? Then we have a fixed point a. This is fixed, but x is variable, is dynamic. So that's a is fixed, but s is movable. Maybe here, and here, and maybe here. Okay. So we define a new big f of x. If the function is positive, it will be much easier to explain. If function is positive, you can regard the result. You can regard the result. If I define it as this, f of x will be the area, right? You can see, we can regard f of x will be the area for the function in the first quadrant and under above the x-axis from a to x. If I define the big F is this one. Please notice f small f is about this one, but big F is about this one. 注意哦，这一步一来，这个在讲微积分基本定理是很重要的概念哈。我现在给你一个函数叫 f of t， 因为等下 x 会用到，所以你会发现，老师你怎么不用 x， 怎么用 t？ 它是 f of t， 是因为等下 x 可以用在这里。好，我就给 y 的 f of t 画出来是这样。我又定义了一个叫大 f of x 的，被定义成这样，怎么定义成这样 ？a 是固定的，中值于 x 是变动的，对 f of x 做解，这个不用 f of x， 应该用 t 的啊。Sorry, here we should use t instead of x. T dt, right? So big F is talking about the area from A to X under this curve. Okay? So based on this idea, if I try to differentiate it, what is the result? Let me just emphasize it again. I give you y is f, small f of t first. Based on y is equal to small f of t, then I define a new big f of x as the integral from a to x f of t dt. And the start point is a, which is fixed. The endpoint is x, which is variable. Okay, so if so, I try to differentiate it, what will happen? So if I want to do that, I'm trying to do f of x plus h minus f of s. So did you remember when we just talked about differentiation? We need to go back to the original definition about f of x plus h minus f of x, then over h. And then finally, we just take limit. Did you remember? If you forgot, please just go back to chapter 3, right? If you want to differentiate this one, we are talking about try to get the limit as h is approaching 0, f of x plus h minus f of x over h, right? So let's just calculate this first. So this is just talking about it. Okay, let me just show you again. Sorry, should be t, right? Should be t and y, and still y is equal to f of t. So still here is fixed point a. So if we calculate f of x plus h, so s is, if x is here, suppose the x plus h should be here, right? With h distance. So if we want to take f of x plus h minus f of x, we are talking about, let me show you, maybe using different color. Here is this one, right? And here, f of x should be from here to here. Should be this one, right? When we just do f of s plus h minus f of s, we are talking about the whole part is talking about this part, right? Can you understand that? X plus h is from here to here. X means from A here. So the part there is just shown here, right? Okay. But when we just talk about this part, f of x plus h minus f of x, we are almost the same as h times f of x. How I say that? Here is h, right? If the h is small enough, h is just a very small, very thin rectangle. 如果这 h 很小，这 h 很小，其实它的这个面积的大小相当于差不多了哈，会等于这个 h 去乘以 f of s 的高度。因为很小的时候，其实它们两个是很接近。这不是一个很严谨的证明，但是约略可以从这看出来哈。When h is very small. So if so, we just use h of s to replace this one. Then you can see h, this h and this h can be cancelled together. So that you can see will be f prime s will be limit h is approaching 0, f of x plus h minus f of x over h, then h limit h approaching 0, h f of x over h, so we can get back f of x back. So you can pay attention to here, then here. When we just differentiate such kind of defined function, the f of x, when we just differentiate it, we will get the small f back. Let me put it again. This is the small f. We just integrate this function, become a big f. Then I differentiate it. Then finally I can get it back. 小 f of t 是我原来给你函数，我去制造了一个函数叫做从 a 到 x 这样的积分，变成那个大 f of x。在这样的定义之下，我刚一路有把这些图画给大家看，对不对？啊，是这样的一个概念，现在推出来之后，哎，把它微分回到原来的微分的这个定义里面的时候，它应该去算这件事情的，当 h 趋近0，对不对？竟然会等于回来原来的 f， 所以这就是微积分基本定理的 Part 1， 就是你把它的做了积分，再对它微分，它就回到原来的函数。所以后面我们讲到积分跟微分，它是一个反向的运作，就像正负加了5减了5，它又回来原来的；乘除乘了5除了5，它又回来原来的。哦，所以它是一个两态，这两态是互为反运作的。OK， then 看一下 ，I need more. Oh, sorry. Okay. I need to erase. Okay, and then we will move to. I just want to give you a formal description about the fundamental theorem. Wait. I remember I have a. I know this way is very stupid. Suppose I can just create a totally new slice. I just don't know how to do that. You know, to save the money, I just use a free version. If they just force me to pay more, and then you can get more function, I just reject. 这个软体还蛮好用的，但是它就是那个有没有？我这边画笔啊，我不是这家公司的哦，但是我觉得还蛮好用的，而且是免费的。是有一次我在上暑修课的时候，有一个同学跟我推荐的，我后来用着就好几年就用下来。它只有一个缺点，就是这里哈，如果你要更多的笔的颜色的时候呢，你要付钱。我到目前为止发现这个，所以还好，我只是控制在几个笔的颜色，所以我都不用多付1毛钱。我常常说我们实验室没有那么穷了哈，但是钱要用在该花的身上。Okay, so let me just summarize. Let me just summarize the theorem that the so-called fundamental let me just finish this part, then we just theorem of calculus part 1. Fundamental theorem calculus part 1. So if f of x, the small f of x is continuous on AB, then we define a big function f of x is from a to x. Remember, x is fixed. A is fixed. X is variable. The new function will be still continuous on AB. And this function will be differentiable on AB. And the last one is the most important thing is its derivative. The derivative is f of s. So that means if you just try to differentiate this big F, you will find you can get f of x back. So you can see I try to differentiate the big f of x, then you can get the small f of x back. This is the fundamental theorem of calculus is part 1. So of course we have part 1, then we have part 2. Okay, so maybe let's just call it a day. See you next week.